Welcome back to the Make Space Boring show. I'm here with Dr. Paul McCartney, Gordon Roesler, past DARPA program manager. And we were just chit-chatting about that before we started. So Dr. Roesler here is a past DARPA program manager. He's the founder of Robots in Space and a worldwide celebrity authority on robotics in the space field. Everywhere I go, Australia, Africa, someone has talked to you and you have helped them. So I really appreciate that. So you came out with a paper recently and emailed it around to your contacts. And so I wanted to do a quick episode here to give you the chance to talk about it a little more and let more people know about it. It's called the Robotic Space Station for the 2020s. I'm going to link to it in the description below. Also, I made the Make Space Boring conferences that we had earlier in the year, which you spoke at. Free to access now for anyone. They can just go to the link and sign up at Thinkific. And on the resources page, there's a resources page of papers and presentations linked to in there. I've also included it there. So people can come and get your paper, sure, wherever.
Let me thank you for being a resource, a place where people can go and get a tremendous amount of information about new space. There's a lot of scattered venues and scattered conferences and this sort of thing. The fact that you're pulling them all together is really great, and I just wanted to thank you for that.
Well, you're welcome. I hope more people take advantage of it, because you would think there would be more traffic than there is. We'll just have to keep talking about it, I guess, and more people will show up. So you were talking about in this paper the idea of updating a robotic space station design for the 2020s. Why now?
It goes back to a concept of how to change the whole space architecture, and the concept is modularity. Right? Today, everything we send up there is fully integrated and functional, and of course, it's also never maintained and never upgraded and never repaired and that sort of thing. Which is why DARPA several years ago started this program called Robotic Servicing of Geosynchronous Satellites. Let's inspect things, let's maintain them, let's repair them, let's upgrade them. And this is along the same theme. But one of the problems with satellites, we build them to last a long time, but stuff changes after you launch them. Technologies change, situations on the ground change, customer demands change. So we want to be able to update spacecraft more quickly to respond to those sorts of things. A way to do that, probably the best way to do that, is to make spacecraft more modular, allow you to put new things on, take things off if you need to. And along with that, and the advantages of modularity are huge. One of them is you can expand your industrial base. People who aren't experienced enough to build a fully integrated satellite can still build modules, which are safe and useful up in space. And so you can get more people contributing. And it cuts down on these single points of failure that we often have in the space supply chain. Another advantage, it goes to the launch infrastructure. Right? Today, you charter a launch vehicle for a particular payload. Say, this payload is going to be done in 2 years. It's going to be ready to fly. So I'm going to make a contract with a launch vehicle to send it up there. If the payload's delayed, the launch is delayed. Right? And so everybody's costs go up because of those delays. What if you could send up things pieces at a time as they're ready and put them together? So modularity is a huge thing. This space station design is all about modularity. It's a place where you can plug in modules and give them power, give them pointing, give them communications, and so forth. So the why now is all the technologies that are involved in this particular design are off the shelf. There's nothing there. There's nothing in the conceptual design that requires laboratory research. Right? It's pretty much someone could start this tomorrow to push that modularity concept forward. Number one, and number two, which I think we're going to talk more about later, the space station, the International Space Station, is not going to be there forever. Right? The NASA's focus for human space exploration is going to shift to the cislunar environment. but there's a lot of important things to be done in low Earth orbit. It's the most inexpensive orbit to access. So if you have a place to do useful things in low Earth orbit, and so the idea is, let's think of as many things we can do in low Earth orbit without humans, and then build a station that supports those needs. So that's the why now, thinking ahead to the end of the International Space Station and pushing on this modularity concept, which is going to have so many benefits across the community.
Right. And I am in total agreement on the modularity. I love it. It is so important. It helped America win World War II, as a matter of fact. The tanks and the airplanes were made with these modular parts. And so some farmer with a milling machine out in Kansas could make a part and send that into the factory and get paid for it, stimulates the economy. The part works on the machine, and out in the field, it makes repair so much easier, and upgrading, like you say, we realize.
There was a recent NASA satellite that was modular. It was called LADDI. It was a lunar research satellite. It was not upgradable on orbit, but it was modular in the sense that people built subsystems, guidance and navigation systems, sensing system, that sort of thing, and plug them into a bus. It's not a big stretch to see how you could use that concept on orbit to take things out, put things in, and it's been demonstrated. In 2007, DARPA had a space experiment called Orbital Express, and that was a modular satellite. It had a battery module, it had a processor module. Both of those were replaced on orbit, and they worked.
Yeah, and I love this idea. And from the car industry, same thing. As consumers, we're all familiar with automobiles. There are third-party parts manufacturers that make a thing cheaper. They make it to a spec, and it fits and it works. And they can customize a little bit and make some neat bumpers or something like that. But like a headlight, for example, is a very straightforward thing. We can get the brand name one, or we can go out and get a third-party modular one. Same connector, pop in and out, no trouble. So what argument are you making? What will this robotic space station be able to do? It looks like, or it sounds like it's partially as a successor to ISS or not. And in the paper, your section 3 alternative system concepts, that was the most interesting part to me personally.
You could make a robotic space station to do a lot of different things. It could focus on assembly. It could focus on experiments with robots. Science could be the main focus, or testing of things that you plan to put in large constellations. You want to get them a little time on orbit and that sort of thing. I selected the idea of hosting these modules as just a concept that would allow me to do a crude business case analysis, right? I said, this is one I understand. This is one we can talk about. It isn't the only thing you can do, but this particular paper is about a robotic space station based on launching small modules that have an instrument or a test cargo or something like that, and plugging them in. And there are a lot of customers for that. NASA always has things they want to test before they spend a lot of it. In the commercial industry, if you're going to build a constellation of thousands of satellites, you might want to test some of those components before you commit to them and that sort of thing. The military has things that they want to test out in space. Just sensors, communication systems, and that sort of thing. And they're also thinking about large constellations in orbit. It isn't just Starlink and OneWeb. The U.S. Space Force and the Space Development Agency are thinking along those lines as well. So this particular design in this paper is all about hosting modules. And of course, we do that on the ISS. We have the external pallets. And those have been very successful in getting things to space quickly and cheaply.
Okay.
So that's the kind of function I'm thinking about duplicating.
Right. Okay. So getting some focus. There are already built-in customers for this because people are doing the thing already with a different platform and that. You've talked about in the paper, you've done some financial modeling. You are the first to admit in there it is incomplete. You talk about $500 million to $1 billion investment somewhere in there. I'd like to hear about a couple of big assumptions you built into the model and what people should be thinking about when it comes to the math.
There's there are a lot of assumptions in there. I tried to write down as many as possible in the paper for clarity. Well, one of them was, okay, I'm not going to start spending money on this until I have some signed contracts for hosting modules, right? To get a little bit of not necessarily that they start paying you before you've even built it, but require some payments earlier than after I'm on orbit and that sort of thing, to try to smooth out the CapEx curve a little bit to bring it up. Is that realistic? I don't know. I'm really only asking for like a 1-year advance in the payments, but maybe that's too far to climb. I don't know. Another was that the lifetime of the thing is very long, in excess of the period that is required for return on investment.
Right.
It seemed as though you could get your investment back, and we haven't really talked about where is this money coming from and that sort of thing. But, it seemed as though you could get return on investment in about 7 years of on-orbit operations, which means more like 11 years since the project starts. That's a long time. This is not a venture capital kind of thing. It's an infrastructure play, and infrastructure typically, whether it's a new ship or a bridge or a highway or something like that, it takes a long time to get return on investment. It just does, and this is no exception. But if it survives and continues to function beyond the return on investment, the net present value is very good in this model.
Okay, so it should pay off in the long term, as you say, if it survives. And there is the question of where does the money come from? But this could be a commercial venture. It really could be, particularly for a larger organization that wants that capability range developed, right?
And can command $500 million or $1 billion of capex, right?
Right.
So let me explain for your listeners briefly where the money is supposed to come from. The whole concept was, it's pretty clear technically that we can build a robotic space station. The question is, does it make sense economically? And make sense means not only can I get my return on investment back, but is there some motivation for people to use this facility as opposed to the traditional way of every payload gets put on a satellite and launched it as an integrated unit? The assumption was that you get rid of about 2/3 of your mass and cost by just launching a module up.
Right.
Not only do I have less integration and test I have to do, fewer parts that I have to buy and that sort of thing, but I can use a smaller launch vehicle. And we now have this sort of spectrum of launch vehicles in the 100 kilogram to 1 ton range. And so some of the launch cost is different depending on where you use the old way or the modular way. The space station operator gets a fee from the module owners, right? And the paper goes into detail about the fee and that sort of thing. But it appears that a fee can be charged that gets you this return on investment after about 7 years of on operation, and saves each payload operator owner about 20% of their program costs.
Okay.
So that is a win-win. It's not dramatic. It's not 90%, but it's a significant saving. Right? So that's where the money comes from.
Okay. And I think a commercial organization or a conglomerate or something could raise that much more, get that much money. This wouldn't, as you say, it's not venture capital. It could be debt financing based on ongoing operations of other organizations. We're used to in the space industry, especially on the commercial side, dealing with smaller numbers, millions of dollars, tens of millions of dollars. $100 million is a lot of money in commercial space. But if you look at like WeWork and SoftBank and that debacle, that was a great deal of money. I mean, that was $1 billion plus or whatever, right? And so what I'm saying is that folks in financial markets outside of space are actually used to dealing with larger amounts of money. And so while we might look at $500 million to $1 billion as scary, There are many other places in the world, where the thinking is, yeah, okay, let's do it, right?
Sure.
It's not as big of a deal. So it is possible. Let's finish up with this, Gordon. We've talked about modularity, launching smaller pieces, keeping the weight down, and then it goes up and it kind of hooks on to this existing robotic space station that we're talking about, and then we can test or do our experiment or whatever with it.
Quick interruption there. One part of the system that I have in the paper is a small local transfer vehicle, so that every payload that comes up doesn't have to be equipped to do rendezvous and proximity operations. Right. So when the Dragon and the Cygnus go up to ISS, they have a series of lasers and cameras and software and all that sort of stuff. That would be a killer for the module owners to have to pay for that. So the $500 million includes this small local tug, if you will, that goes and gets a dumb payload and brings it over the station. Just wanted to get
so
that.
we are. That is an important thing to point out. And that helps answer this final question then. Can a robotic space station truly be designed to maintain itself without human interaction?
Hopefully, and there's 3 different approaches to that. One of them is redundancy, right? So getting as many robot systems in there, knowing what the failure rates are going to be so that you can still keep going for those years and years. A second is replaceability. So if the robotics are designed, and everything on the station are designed to have that same modularity that the payloads do, then if you have a failure, you should be able to go do that. And the third is simply the most expensive option, which is exquisitely designing these things to last forever at obviously tremendous cost.
Okay, well, fantastic. Gordon, where can people reach out to you, find out more? I know you've got a website.
Right. The website robots-in.space has a contact feature in it. I really do look forward to people's questions.
All right. Well, thanks for doing this. I appreciate it.
I appreciate, and again, I appreciate what you do, Jason. Thanks a lot.